So, welcome everyone to this week's Origins Colloquium. It's a great pleasure to have Roberto Maialino visiting to give us this talk remotely here. And Roberto received his PhD from the University of Florence in 1996, with also a visit secondment to University of Arizona at the time. He was a postdoctoral fellow at MPE in Garching for a year or two, and then was back at Archetri Observatory as a researcher there until 2012, when he joined Astronomy Observatory in Rome. And then after that, he joined the University of Cambridge, where he's now a full professor there. He's pioneered a lot of work, of course, in the high redshift universe, and recently has been spearheading the efforts to understand what's really going on with these black holes that James Webb is finding. He's found a lot of them in the very high redshift universe. So he has also an honorary appointment at UCL and is a fellow of the Royal Society now, and is really, I think if any one person is leading this field here, it's Roberto's right at the top here. So we're very happy to have you giving us a talk on this topic, Roberto, today. Thank you.
Thank you very much. Thanks for the invitation. It's a pleasure to give this presentation, especially in these exciting times where we are finding a lot of new and interesting and puzzling results on the early universe, especially in the area of black holes. So I understand that this is probably a broad audience, so I will give you an introduction to the topic and then go more deeper into the specifics of what is found with Webb. So I think that we all agree that one of the major scientific achievements of the last century has been the unambiguous proof of the existence of supermassive black holes at the center of galaxies. And this, of course, not unexpectedly gave the Nobel Prize 5 years ago. However, except for a very few mostly local cases where we can infer dynamically, directly, the presence of supermassive black holes and measure directly their masses, the vast majority of supermassive black holes are inferred indirectly by when they're in the active phase of accretion through the glow of their accretion disk and the surrounding photoionized gas. And in these cases, they are called active galactic nuclei or AGNs, secret nuclei or QSOs, depending on the luminosity. And the typical spectral energy distribution of AGNs is characterized by a prominent blue bump with a lot of ultraviolet radiation associated with the accretion disk, but also a prominent tail in the X-rays, which we think is produced by hot corona surrounding the accretion disk. And then this energetic radiation photoionize the surrounding medium, which we see in a forest several emission lines. And we typically distinguish two main parts of the ionized gas. One is the so-called northern region, which is essentially ISM in the host galaxy, which has been ionized by the AGNs with relatively small velocity expression, typical of the host galaxy, except that might have some outflows, of course. And then there is a much more compact ionized region, the so-called broadline region, where very likely in the sphere of influence of the supermassive black hole, and we see these through these very broad lines, which are mostly broadened by Doppler motions and by Doppler effect. And these clouds are extremely dense, density higher than 10 to the 9 atoms per cubic centimeters. And so therefore we see them only in the lines which are permitted for dipole transitions, such as the Balmer hydrogen lines, the helium lines, while the lines which are forbidden for dipole transitions, such as these oxygen 3 lines, are not seen because these are collisionally suppressed. And of course, we may have this dusty structure called often torus around the central region, and depending on the line of sight, we may not see the broadened region, in which case we call this type 2 AGNs, and if we see the broadened region, we call them type 1. Now, it is also interesting that the local black holes seem to correlate relatively tightly with the properties of the host galaxies, and there are various of these correlations. Here I summarize them with a simple one, which is the correlation between black hole mass and the stellar mass of the host galaxy, particularly the spheroidal component. And typically, the black holes, although supermassive, they account only for about 0.1% of the host galaxy mass. And one of the interesting thing is that these massive black holes have masses of ranging from millions to billions solar masses. So one of the most important questions of astrophysics now is to understand how these black holes manage to become so big. And the standard scenario is that they started with stellar remnants, and these then created surrounding matter, and then grew and grew across the cosmic time until they became supermassive. However, here the accretion phase, there is a bottleneck, which is the Eddington limit, so the theoretical limit at which the radiation pressure due to the light emitted from the accretion disk, or the energy, generally gravitational energy converted into radiation, essentially is compensated by, they compensate the gravitational pull. And so, in principle, black holes cannot exceed this accretion limit. Now, if you want to test this scenario, you have to go back in time and trace this pattern across the cosmic epochs. That is, when the formation of the black holes in the early cosmic times, and then their growth across the various cosmic epochs. And for doing this, we have to look back in time, and for the James Webb Space Telescope is probably the most powerful time machine that we have, because it's extremely sensitive, and it allows us to see very faint distant objects, and therefore back into the past. And the leap in sensitivity provided by Webb is really amazing. In some bands, in some near-infrared spectral windows, the leap in sensitivity, especially in spectroscopy, is even more than 3 orders of magnitude. And this is amazing because it happened very rarely in the history of astronomy, and more broadly in the history of science, that you had this gigantic leap. I like always to compare this in the visible to the being equivalent of instantaneously upgrading Galileo's telescope to modern large telescope. It's just that kind of impressive leap. And of course, when you open such a new discovery space, you find you expect to find a lot of new things, and indeed the JWST has not disappointed. And there's been a lot of exciting and also very puzzling new results that have been obtained by Webb. And these are just a few of the spectacular findings by Webb, and again, very intriguing. And I will not have time to discuss most of them. I will focus on the bottom point, that is the findings about the black holes. And particularly, as you will see, it seems that there are too many, maybe too massive too early, as you will see, maybe too naked, and maybe too weird. And so let's look into this. So this is so JWST has indeed found several intermediate or low luminosity agents in the early universe, and in terms of imaging, they are not particularly spectacular, are just very compact sources. But in terms of spectroscopy, they are fantastic. This is one of the spectra obtained with Webb. And the signal to noise is so high that you can see we had to plot the flux, the y-axis, in log scale to see some of the noise. Some of these lines have signal to noise higher than 1,000. Okay, and we see these high ionization lines, which are characteristic of the Northern region, but also, most importantly, these very broad lines, which are essentially tracing the broader region typical of AGNs. And with Webb, as I mentioned, we have opened a totally new discovery space for this class of objects. In particular, we are tracing black holes, AGNs, that are much less luminous than the quasars that were found before JWST, and therefore either lower mass or lower accretion rates, and also pushing to higher redshifts. Now, one of the first interesting finding is there, as I mentioned, there are a large number. As you can see here on this diagram, this is the UV luminosity function of AGNs as a function of UV magnitude. And you see that the population of black holes that has been found by JWST is 1 or 2 orders of magnitude higher than the extrapolation of the luminosity function of luminous quasars that was found before JWST. And this is such a high number of black holes, of AGNs, that has resulted into a revival of models where ascribing to the AGNs a significant contribution to the realization of the universe. And there have been models ranging from a contribution of 20% all the way even to dominating the realization of the universe. I don't have time to discuss these aspects, but this is certainly a very exciting possibility. Then, from the broad lines in the type 1 AGNs, assuming that this is driven by the motions of clouds around the black hole, and assuming that we can infer the size of the broader region from a scaling with the luminosity that is being, calibrated locally through various techniques, in particular reverberation mapping, we can somehow estimate the black hole mass from the luminosity and the width of these broad lines. These are the so-called virial relations, and their applicability at high redshift and the new class of AGNs found by JWST is debated now, but we'll discuss this in a few minutes. So if you take this assumption, and you can measure therefore the black hole masses and also therefore the Eddington luminosity, and here you can see a now outdated diagram that, because this is, I think, is from more than 1 year ago, where you should see the luminosity relative to Eddington as a function of black hole mass for the new class of AGNs found by JWST, and compared with the population of quasars identified from ground-based telescopes before JWST. And you see that with Webb, we find much lower mass black holes, but also the dormant counterparts of high redshift quasars, which were identified before JWST. Now, these are, as I mentioned, we are finding black holes all the way to very high redshift, and these are some of the most distant black holes. And you see that they are already very much massive, with millions, several million solar masses already in place around redshift 9 to 10. And you see these blue lines try to trace back the evolution of these black holes, assuming that they have always been accreting at their maximum rate given by the Eddington limit, okay? And you see that even in this most extreme scenario, it is not possible to explain these black holes so massive so early with the standard scenarios of stellar remnants that have been accreting below the Eddington limit. So there have been various theories, alternative scenarios that have been proposed. One is that black holes were born big. This is the so-called heavy seed scenario or direct collapse scenario, whereby maybe pristine clouds of gas under certain conditions collapsed without fragmenting and resulting into a very massive protostars, which soon collapsed into a very massive black hole and at that point, with some accretion, you produce a supermassive black hole. Another possibility is that in the very dense environment of the center of these protogalaxies, nuclear star cluster managed the star-star resulted into rapid merging, runaway merging, which resulted into the rapid formation of intermediate mass black holes, which then again through some accretion resulted into supermassive black holes. Another possibility is that the seeds were indeed stellar remnants, but that these seeds somehow managed to, were sort of reckless, managed to overcome the Eddington limit, at least in short bursts of super Eddington accretion. And in these cases, these short bursts, although possibly very short, managed to boost the mass of the black holes very rapidly to possibly supermassive values. Here there are several, I would say dozens, if not hundreds of these models that have been proposed. And I'm showing here only a few of them. And you see representative of the three categories. And you see that in somehow with these models, you can indeed reproduce these early black holes. And discriminating between them is not easy. Different black holes actually can be reproduced with the specific properties with different models, and maybe all of them applies to different categories of black holes. And we need, how to say, other properties to discriminate between these models. One of these is the X-ray, the spectral energy distribution, and particularly the X-ray properties. One indeed very puzzling finding about the JWST discovered agents is their extreme X-ray weakness. And you see this in this diagram, which is showing the ratio between the bolometric luminosity to X-ray luminosity as a function of bolometric luminosity. And you see that most of the newly discovered, so this is the local relation, this line for normal optically or X-ray selected agents. And you see that the colored points are the JWST discovered agents, and essentially nearly all of them are lower limit, which means upper limit in the X-rays. And even their stack is essentially results in non-detection well above what is expected from normal agents. And this is the case both for type 1 agents, for type 2, and for mid-infrared selected agents. So whatever is the selection method, all of the vast majority of the newly selected, the newly discovered agents by JWST are extremely X-ray weak. And there's been two broad categories of scenarios to explain this X-ray weakness. One is that maybe due to extreme absorption, in particular if you have an absorbing medium along the line of sight, which is has column density larger than a few times 10 to the 24, that is Compton thick, you can suppress heavily the X-rays. The point is that this medium has to be relatively dust-free because we still see the broad lines. And for instance, the broad line clouds could simply be this medium which is absorbing because they are indeed Compton thick and dust-free because inside the sublimation, the dust sublimation radius. Another possibility is that these agents are intrinsically X-ray weak, maybe because missing the corona, or because the X-rays are somehow beamed. And these scenarios are expected in the case of high accretion rates. For instance, the so-called narrow line secret ones in the local universe do tend to have these kind of properties. And these narrow line secret one indeed thought to be highly accreting black holes. And this illustrates the scenario of super Eddington accretion, mild super Eddington, where indeed you expect that this prominent X-ray emission is much lower, especially for specific viewing angles. And so these, especially at high redshift, where this distribution is shifted to lower energy, can explain the lack of detection. On the other hand, in the scenario of heavy absorption, there are some findings that also support this other scenario. This, for instance, is a new stacking which we have obtained with the group of Andrea Comastri, where the stacking has been now done in rest frame energy, and now there is a detection at very high energies, between 10 and 30 kbs, while no detections at lower, softer energies. And so this is just what you expect in the case of a normal AGNs, which is heavily obscured by a comptotic medium. So it goes in that direction. In the same context of absorption, another remarkable finding is the detection of absorption in the Balmer lines, in particular H alpha and sometimes H beta, in quite a remarkable fraction of these early AGNs. And the detection of H alpha absorption or H beta absorption is actually quite intriguing, and because to get H alpha or H beta absorption, you have to populate n equal to the n equal to level of hydrogen. And so you need high temperature, and that's not a problem. But being this a short-lived level, you need to keep it populated, and to do so, you need a very high density of gas and or high column densities. And this can happen essentially, it requires typically what we find densities higher than 10 to the 9 atom per cubic centimeter, which are essentially the densities of the broadline clouds. So one possibility is that what we are seeing is indeed this dense gas along the line of sight, possibly clouds of the broadline region, which on the one hand are resulting into this H alpha and H beta absorption, and the other hand can result in this Compton thick X-ray absorption. This finding about the absorption is also connected to the famous population of the little red dots. Now, there is this widespread misconception that all AGNs found by JWST are little red dots. That's absolutely not true. Only about 10 to 30% of the AGNs discovered by JWST are these little red dots, which are characterized by these typically broad lines, okay, but these red optical colors are compact. Red optical colors are typically these V-shaped continuum shape, and a number of them also by a prominent Balmer break. Now, this Balmer break has been quite puzzling because it's typically associated with evolved stellar population. We see a lot of galaxies with this prominent Balmer break. The problem with the little red dots is that you really ascribe this to evolved stellar population. The stellar masses that you infer are very large, and to the point that some teams have claimed that they are cosmology breaking, in the sense that such large masses so early in the universe are essentially impossible to form, even assuming an efficiency of star formation of unity. Okay. The other problem is that these objects are so compact that such large masses result in extremely high stellar surface densities, even higher or comparable with the stellar surface density of the nuclear star cluster at the center of our Milky Way, but orders of magnitude more massive. So this is very uncomfortable. However, one point is that these Balmer breaks may be actually associated with the Balmer absorption that we see in the Balmer lines. And indeed, if you have H alpha absorption and H beta absorption, by simple atomic physics, the absorption doesn't stop there. You must have also H gamma absorption, H delta, and so on, all the way to the Balmer break. Okay, so simply by atomic physics, the presence of these Balmer absorption lines must somehow result also into a Balmer break. So what we had proposed is that actually the Balmer breaks that we are seeing are not associated with stellar population, but are due to dense gas along the line of sight, which is the same gas that is producing these Balmer absorption lines. And this was initially postulated in this paper by Koei, Ayoshi, and myself, and was first demonstrated in this specific target through this Black Thunder large program. It's a large program with the Webb led by Hannah Hubler and myself, and where we observe these prototypical little red dots at high spectral resolution. And in H alpha, we see this prominent H alpha absorption. And if you derive the expected Balmer break from this H alpha absorption, you get a break which is indeed fully consistent with what observed. Not only So indicating that this Balmer break is actually originate from dense gas absorption. Not only, we also detect this narrow H alpha component coming from the host galaxy. And from this, we derive a dynamical mass of the host galaxy, which is an order of magnitude lower than the stellar mass that you would derive, assuming that the Balmer break is stellar. So this is an unambiguous proof that this Balmer break doesn't have anything to do with stars, is actually due to dense gas in embedding these little red dots. And so the stellar origin of these Balmer breaks, therefore, greatly at this point relaxes all the tensions associated with large masses and extreme stellar densities. And this evidence for non-stellar Balmer breaks has been found even more prominently by the detection of these Balmer breaks, which are even more prominent and larger than what you would expect from any stellar population that have further induced to the presence of these presence of dense gas around, extremely dense gas absorbing the light of these accreting black holes. Now, these results have, triggered the development of a plethora of scenarios from dense atmospheres of neutral and ionized gas embedding the accreting black holes and the broadline region, or vice versa, this envelope being around the black hole and the accretion disk, but inside the broadline region. I don't have time to go through all of these scenarios, but my simple approach is that I don't think there is the need to invoke any new exotic scenario. I suspect that all the properties that we see are simply explained by the broadline region where the clouds have covering factors much larger than what's seen in local AGNs. And I think that's, to me, the simplest explanation also by observations, because we use a scenario that is well tested locally. It simply implies, an extension of this scenario. But I don't have time to discuss this because it becomes very technical.
Well, we can come to it in the discussion, perhaps. Yeah, I'm sure it'll come up.
Yeah, okay.
Great.
So maybe I skip the nitrogen abundance because running short of time. One other interesting finding about these early black holes is that when you plot them on the black hole to stellar mass relation, they are typically very overmassive relative to the local relation, and by 1 or 2 orders of magnitude. Some of them are nearly as massive as their host galaxies. So now there is a lot of discussion about how much of this is due to selection effects, and certainly selection effects play a role in the sense it's more likely to detect these more massive black holes. But honestly, I don't think this is very important in the sense that even if this is only the tail, it's just amazing that somehow the universe managed to produce these monsters in these tiny galaxies. And this is highly informative for the seeding and formation scenarios of these black holes. And indeed, there have been multiple models. These are just 2 of them proposing to explain this seeding with bursts of superadditive accretions or heavy intermediate mass black holes and so on. However, before going to all of these interpretations, there has been a lot of discussion on whether these black hole masses are reliable. And in particular, we are using these virial relations that are calibrated locally, but there's been claims that if these are accreting super Eddington, then the black hole masses may be overestimated by a factor of a few, or in other scenarios, if super Eddington, they are maybe underestimated by orders of magnitude. And then there's been this sequence of models of where the broadlines are actually due to scattering of in this putative atmosphere around black holes, which may result in actually overestimating the black hole mass by a large factor, and this has been disputed in various ways. I don't have time to go through all of these, but I think a breakthrough in this area has been the direct black hole measurements in these little red dots at epoch of ionization, where we leverage the gravitational lensing to measure the motion of the gas around in the vicinity of the black hole with integral field spectroscopy. And in this case, we find a perfect Keplerian rotation curve around the supermassive point mass. And therefore, it looks like we are essentially measuring exactly the mass of the black hole, which turns out to be perfectly aligned with what expected from the local albedo relations and in conflict by orders of magnitude with what was expected by these other scattering scenarios. Just to mention that in this case, we can therefore estimate very tightly the Eddington luminosity, and therefore this black hole is accreting at sub-Eddington by a significant factor. And not only we can obtain the Keplerian rotation curve is so perfect that leaves very little room for any galaxy around it. We can put a very tight upper limit on the mass of the host galaxy, and we can infer that the black hole is certainly more massive than its host galaxy, if there is a galaxy at all, because we don't see any evidence of this. And we have nicknamed this as a sort of nearly naked black holes. So in this case, it seems that the black holes formed well before or much faster than its host galaxy. So this, I think, is a major paradigm shift. And the other interesting finding on this black hole is that we could measure also the metallicity of the environment in which this black hole lives, which turns out to be extremely low. We barely detect any oxygen emission, and we infer metallicity well below the 1% solar. Now, these properties now provide some very good constraints on these black holes in terms of black hole mass, black holes to stellar mass, and metallicity. And most scenarios struggles to explain all of these properties simultaneously, although we haven't explored all possible scenarios. One interesting possibility that I didn't discuss earlier on, but which has been proposed recently more and more, is the scenario of so-called primordial black holes, that is, black holes formed very soon after the Big Bang in fluctuations, soon after the inflations. And these were not taken too serious until recently, but in the last few years, there's been a surge of papers modeling these primordial black holes, especially as a consequence of the results from the gravitational waves from LIGO, but also the results from JWST. And if I plot some of these scenarios on the constraints that we have on this black hole, this actually seems to fit reasonably well. I'm not saying that we are obtaining evidence for primordial black holes, but I think these prompt us to be, how to say, open-minded. I will skip the part on the merging of the black holes because I think I'm out of time. But I would just finish by saying that, okay, you may ask, I've shown various lines of evidence supporting different scenarios, supermassive heavy black holes, heavy seeds, super Eddington accretion, maybe primordial black holes, merging of black holes, nuclear stars, and so on. So what is in the end the origin of these black holes? I don't think that, however, one should get fixated in trying to identify the one single scenario explaining all black holes. I think that the more I study these, investigate these new results, I think that all scenarios are possible, all these mechanisms are probably at work in the early universe, and the different scenarios are probably responsible for the formation and growth of black holes in different environments, at different cosmic epochs, and in different evolutionary stage of their evolution. So I think that probably most of these scenarios are actually really working for, and a plausible explanation for the formation of these supermassive black holes. And I will stop here. Thank you.
Great. Thank you very much, Roberto. We have plenty of time for questions and discussion. I know you jumped over a few topics, so we can potentially just come back to those. So Ryan and Virginia, you can help me if there are questions there, or in Zoom, just raise your hands, or here. Perhaps let me start off on the last point then on metallicity. you showed a very nice example of this particular source, which is special because you've got a rotation curve and a good mass. But assuming the masses are fine, how many systems now have metallicity measurements that you can do a good, a study that, because this, as you showed, it rules out a lot of scenarios having this very low metallicity.
Yes. So at lower redshift, well, measurement of metallicity in this class of agents is not easy because you have to uh, recalibrate the metallicity indicator properly. But let's say at lower redshifts, most of these agents are already, as you say, relatively metal rich, so around 10% solar. At redshift higher than 7, is still very much unclear. Let's say we discussed in the paper that about half of the agents found at redshift higher than 7, and by half I think we're talking about 3 or 4, have relatively high metallicity, high, I mean 10% solar, and so they would fit well with many of these scenarios. While the other half, I think another 2 or 3 seems to share similar properties as QSO1, that is extremely low metallicities, although it's not possible to say yet because in a few of these we need high aspect resolution observations to disentangle the narrow component of H beta from the load component. So we
Are you
have
able to measure? Are you able to measure the metallicity in the broad component directly, or do you, or you?
No, this is something we are trying, but well, in some of the in quasars, yes. Well, yes, sorry. There are various models where, because there we have multiple components, carbon 4, nitrogen, and carbon 3, and oxygen 3. And there are various models where they constrain the metallicity of the proton region, and this turns out to be typically fairly high, of the order of even solar. But these are sort of the extreme of the population, are the very luminous, very massive, probably have undergone very quick evolution. On the lower luminous population, these I don't I think there are studies which are starting to try to do this, but has not been done yet properly. Yeah.
Mm-hmm. But wouldn't it be easier to do in the broadline region?
Not really, because in principle, yes. The fact is that the primary traces of the metallicity of the proton region are the UV transition. So carbon 4, nitrogen 4, or carbon 3, magnesium 2, and oxygen 3, and helium 2. And these are, well, to begin with, are not so simple to model because many of them are resonant lines, and so there are a lot of radiative transfer to take into account. And observationally, they are in the blue UV part of the red frame spectrum, which is typically in the region where JWST is less sensitive. And so there are detections, but often with the prism that is the very low resolution. So in that case, we can't resolve whether it's coming from the northern region or the broader region. But yes, potentially it's feasible, but I wouldn't say it's easier, let's say.
Mm-hmm. Well, it'd be nice to do a check in this QSO1 maybe with the.
Yeah.
Yeah. Well, Ackland, please go ahead. Question.
Hi, Roberto. Great talk. So you skipped the part on the merging black hole at high redshift. So I
Yeah.
was wondering if you could go over that a bit.
Yeah,
For
let
2
me,
minutes or so.
sorry, share again.
And I was
So
also
the
interested in
other, yeah, sorry, I tried to stay in the half an hour.
Yeah,
I
that's
was
fine.
I was ambitious. So this is in a number of these, especially with the integral field spectroscopy, in a number of these high redshift agents, we find evidence for two black holes, accreting black holes, essentially in the same galaxy, separated by a few hundred parsecs. This is one of these cases where especially this black hole here with this broadline region is offset by about 600 parsec. And then we are finding a few more. This is
Okay, can I just ask about this offset? So the evidence here is just that it's offset, or is there evidence for two components in any sense?
So in this case, it's the broadline region of this AGN is clearly offset, and actually has also continuum associated with it with respect to the core of the galaxy, which is traced by the stellar continuum and also the velocity field. And we think there is another black hole here, traced primarily by the Narn lines. The Narn line ratios in this central region are typical of the excitation of AGNs. So let's say in this case you have a broadline AGN offset and the narrow line AGN in the core of the galaxy, of the more massive galaxy, which is probably maybe obscured. And then and then there are a few other cases that we are finding and in the process of analyzing or publishing. I think this is also really remarkable because there is a clear AGN in the center of the galaxy, and this was well known before our observation by traced by this very broad component of the H alpha. And then with the integral telescope, we found this second black hole with this BLR offset in this case by 1.7 kiloparsecs, and extremely nice. And then there is this wing here, which initially we thought that it is maybe an outflow or something like that, but there is no counterpart in oxygen 3 or other forbidden lines. And therefore, the most likely interpretation for us is that this is actually yet another small black holes in the process again of merging with the primary black holes. And we see this actually, that this wing is actually offset also with respect to the broader wing. So, but these are particularly remarkable case, but there are a few more which are simply 2 BLR offset or 1 BLR in type 1 AGN, type 2 AGNs. And the finding is that we're finding quite a few of these AGNs, which implies that the fraction of these possibly merging black holes is higher than was expected. And this was already pointed out by previous studies where they were finding that the population of dual AGNs, and by dual now I mean separated by several kiloparsecs, so in the halo of each other, if you want, so well separated, was a factor of 10 higher than was expected by simulations. So it was already going in that direction. But my point there was that it's not clear whether these dual AGNs implies that these black holes really merge, because there are some models, for instance, the blue tide or similar, that predict that these black holes have very long sinking time, so they never merge. Well, the galaxy may merge, but the black holes keep wandering in the halo of the galaxy and never actually sink into the other black holes. But in this case, we are finding these black holes which are actually essentially already in the same galaxy.
In this particular case, this is a secondary black hole. There does not seem to be a strong continuum source there. Is that right, or am I reading that right?
Yeah, well, there is something. This is unfortunately this scale of the image is not great, but there is indeed some continuum which is seen, I think, only in the red part or in the blue part of the filters. So it's I don't remember now whether it's bluer than the main galaxies or redder, but has different colors. But it's seen also in continuum, yes.
Okay. Well, Aklam, did that answer your?
Yeah, I had a quick follow-up. So if you have, like, say, these very close separation black holes, which are maybe not merging, but they're stalled, and you measure the black hole masses, so does that like impact the black hole mass estimates at all? Like, are you measuring the mass of the primary black hole or some combination of the two black holes, or?
Yeah, in this case, we are, I mean, these black holes are still not really in the phase where they share the same accretion disk. Okay, well, I mean, this scenario where you have the two mini accretion disks and then surrounded by a joint accretion. So we are not talking about the sub-parsec phase. These are still on scales of hundreds of parsec separations. So if you interpret these broad components as each the broadline region associated with each of these black holes, then yes, they are not still, how to say, these clouds are still totally dominated by the sphere of influence of the local black holes. They don't feel anything of the very little of the other black hole. And so in principle, they are relatively reliable measurements of the black hole masses if you trust the virial relations. Of course, if then we put in questions the virial relation, but that applies to the whole population of black holes, not specific about these merging systems. But coming, if you I can expand this has been also in the surprise somehow of some of our theoreticians, colleagues, and so on, because for them it's remarkable that these merging things, black holes, manage to keep their gas around them in the merging process, which is important because they manage to keep the accretion while actually they are merging, and there are theories or models that expect instead that may stop accreting in the merging process.
Okay, next topic is
I was a very nice talk. Thank you. I was very curious how many what sort of physical resolution you need to be able to do the dynamical modeling. It sounds like quite strong lensing is required. Is there hope for being able to do this in many other sources, or is this sort of a rare kind of thing?
Yeah, so it's here we leverage the strong lensing. Yes, it's a factor of 6 lensing and 3.5 in shear. Okay. However, is actually the main point in this case is that we hadn't realized this, that if you estimate the already a priori, okay, without going through the mass of the black hole that is estimated from the virial relation, and the velocity dispersion that you see in the narrow lines, which is extremely small in this case, it's about 20 kilometers per second. The sphere of influence, so the black, which is black hole mass g divided by sigma square, is actually pretty large. It's about 200 parsecs. Okay, so it's was not an unexpected result. Okay, it's you did expect to see. Of course, we didn't assume anything a priori. This was a completely, how to say, blind, how to say, analysis. Okay, but the sphere of influence of the black hole in a case like this is pretty large. Okay, simply because black hole mass is fairly large. It's about 50 million solar masses, and the velocity dispersion is fairly low. And there are, and of course, in this case, we are facilitated also by the gravitational lens, which stretch further the scale. But there are a number of other cases where this is still the best, but there are a number of cases where the sphere of influence is also expected to be relatively large and should be resolvable, and we are working on that. An important thing is that keep in mind that the capability of resolving rotation on small scale, you can go actually well below the resolution, okay, if you have enough signal to noise. This is a well-known observational technique that if you have very high signal to noise, you can distinguish in this case, we are using also spectroscometry, for instance, which is not the only technique that you use. It's one of the techniques that are employed in the papers. But if you have very high signal resolution, you can actually resolve even below the resolution. I mean, the proper motion in the galactic center that were done initially by Reinhard Genzel actually resolved proper motion well using a spectral resolution which was well below what's needed in principle, but thanks to the high signal noise, they managed to trace the proper motion. So just
This is the only one with a rotation curve at the moment. How many dynamical masses at this quality or similar quality can we expect in the next few years?
we are working on this, and I think there is a technical problem. If I maybe I enter too much into the technicalities, that this essentially can be done well primarily only with the integral field spectroscopy, that is this slicing of the field of view and doing spectroscopy spatially resolved. And if you compare, there might be a problem of calibration between one slice to the other. And so if you have if you see this kind of rotation perpendicular to the slice, this may be suspicious because maybe simply a consequence of calibration of the integral field spectra. So in this case, it's not a problem because fortunately the rotation is nearly parallel to the slice orientation. That's why we show this orientation here. There are other cases where we see this effect of rotation at the expected level, but in that case, the rotation is closer to the perpendicular to the slice. And in that case, one is much more worried about the systematics in the calibrations of the spectra. So unfortunately, you have to be also a bit lucky that, or essentially plan the observation to have multiple position angles so that you control these potential systematics.
I was going to ask about the little red dots in the Balmer break. Why do we not see low redshift equivalents of these little red dots, or do we?
Okay, this is not true. Is NGC 4151, which is the prototypical Sievert one, actually does show Balmer absorption. Okay, and it has associated X-ray absorption and is variable. Okay, so it goes deep and then disappears, and then you have X-rays which gets stronger, and then the how to say turnover of the photoelectric absorption of the X-rays gets stronger, and this is just fully consistent with the clouds that are passing in front and dense clouds which are passing in front and introducing this Balmer absorption and X-ray absorption. What's happening locally is that, and this was discussed several times, that probably the broadland region is mostly has lower covering factor and is mostly equatorial. Okay, so the line of sight that intersect the BLR are generally also intercepting the dusty medium surrounding it, and so you have a selection effect that essentially doesn't allow you, in most cases, to see the absorption along this line of sight, while you tend to see the clear, view of the emission disk.
So it's because you have a presence of a dusty host at low redshift.
Essentially, yes. And I mean, these in many models, this covering factor of the broadland region is only 10% locally. So in principle, you are expected to see this only in 10% of the cases, and probably not even those 10% because of these surrounding dusty mediums. But if the broadland region is, because more gas in these early epochs, more compact, is actually more randomly distributed than for pi, then you can have many more chances to cross the line of sight of the BLR.
And then a follow-up on this a little bit is, since you have estimates of the densities in this broadline region, have you estimated the outflow rates and compare them to the accretion rates?
Okay, the outflow rate, honestly, I'm I'm not sure about it because these absorption features, okay, are generally only slightly blue shifted, maybe by 100 or 200 km/s. So it's not that massive outflows that we see in these nuclear regions. In a number of cases, they are actually rest frame, and actually, the more we observe at high spectral resolution, the more we find them. For instance, in this case, observed at medium resolution, the absorption features totally disappears, because it's filled in by the blending of the proton component and the other component. You have to go at a high resolution to see it. Okay, so it means that there are probably many more, and so since the high resolution observation are much more rare, there are probably many more of these rest frame absorption of these absorbers out there. And so in these cases, these absorbing medium, these clouds are not really are flowing very mildly, or actually simply lingering around the black hole, or in this case are actually redshifted, which means actually are accreting, are going towards the black hole. So maybe some people have tried to estimate the alpha rates, but my personal opinion is that there is not a big deal of outflows in these systems, and this may be why also we have this large covering factor, because the black hole doesn't manage to get rid of these clouds very easily, and this may be linked to the. By the way, this we also see. Let me show you in the narrow lines.
So the broad line is really an accretion flow, you think?
Well, it's in the many models are actually part of the outflowing. So these many models of the broader region are also that are clouds lifted from the accretion disk, which are then, how to say, ejected. So locally they are more often associated with outflows, but yes, could also be associated with accretion. And so the regime may change, therefore, between these systems at high redshift and locally. I wanted to show you that in the narrow lines, so typically in low redshift AGNs or high redshift luminous quasars, we see these prominent blue shifted wings of the oxygen tree, which is always associated with outflows on large scales. And again, in the new population of AGNs discovered by JWST, we don't see this wing. It's fairly much symmetric lines, and which means that again, also this gas on scales of tens or 100 parsecs stays around the black holes without going anywhere. There is not this big deal of outflows as far as I can say. So, and I think why is that? Well, there are various possibilities. I think that for me, one possibility is that is due to the low metallicity. And when you have low metallicity, you have less line locking with metals ions in the central region, and therefore, which is the prime drivers of winds in local AGNs. You have also in the outer region less dust and therefore less pressure on dust. So it's this may be one of the explanations. I'm not saying that is this is the only explanation, even because I haven't quantified it. But I suspect this may be a factor playing in this shortage of outflows.
Well, we have time for one or two last quick questions, if there are. I was going to ask, what's the latest on the frontier, the highest redshift AGN? I mean, you had a graph somewhere which showed the redshift distribution of some of the well-established ones, but are there candidates at higher redshifts which are under debate or have broad lines or?
Yeah, there was just 1 or 2 weeks ago, one work, for instance, claiming that one of these prominent emission lines, galaxies at redshift 12, is actually an AGN, according to their modeling, is they favor a lot the AGN solution, but whether I think it's type 1 or type 2, it's is still not clear even because the data that they have yet is low resolution. But I think there are more data that are coming or they have already obtained. So this is yes another frontier that trying to find more of these black holes at higher redshifts, and there are maybe a few other candidates that may go in that direction. I'm sure that in the coming months, if not weeks, there will be maybe more claims. Yeah.
Yeah, it's a fast-moving field.
Yeah.
Yes. Very good then. Well, we're at the hour, just past the hour, so I think we'll wrap up now the main part. So thank you again, Roberto, for a great talk and discussion.
Thanks.